Hi, and welcome to today's webinar, ASHRAE 62.1 Natural Ventilation, Learn the Prescriptive Path and Engineered Path for Design. This webinar is hosted by WindowMaster. My name is Kasper Ravn. I'm a building performance engineer at WindowMaster, and I'm located at our headquarters in Copenhagen, Denmark. So here the time is approximately 9 p.m. and I will be today's presenter. Just to start off with some practical information, I actually would like to do a quick poll just to make sure that you can all hear and see my presentation. You should be able to see a poll at the moment. You're also very welcome to write in the chat if you can see and hear me, or see my presentation and hear me. Yes, it seems like everything is fine. Perfect. Now, today's webinar will be maximum 45 minutes, and I will try to keep it shorter. This means we will have at least 15 minutes for Q&A time in the end. Questions are very welcome, and you can ask them anytime throughout the webinar. There's a question panel, so you can ask in the chat, and we will try to answer them maybe during the webinar, but probably at the end. And if we for some reason do not get to answer your question, we'll make sure to send you an answer directly after the webinar. This webinar will also be recorded, and we will send it to you as an email, but it will also be available on our website in the future. So if you have to do something during the webinar, don't worry, you can always watch it later. We will also share the slide deck along with a quick brochure about WindowMaster automation technology. Now, a quick overview of the agenda today. The main focus will be the engineered path of ASHRAE 62.1. We will also quickly address the prescriptive path. To show compliance and describe the engineered path, we will use a quick example based on the CIBSE AM10 method, where we will also show both design and calculations. Just to clarify, when some of the expression I'm going to use throughout the webinar, when I say ventilation strategy, I'm talking about whether the design is based on single-sided, cross or stack ventilation. And when I say top, bottom or side hung window, I'm talking about these type of windows here, which some might call projected. The natural ventilation procedure was introduced in ASHRAE 62.1 2004. And it has been based on very simple requirements, you can say, which also was similar to guidelines that we see in other places. So for example, the opening area should be corresponding to 4% of the ventilated floor area in all cases. So this doesn't take into account the ventilation strategy we're using. The depth of the room is based on whether you have single-sided or cross and stack ventilation. So for a single-sided ventilated room, we can maximum have a depth of 2 times the room height, while for a cross or stack ventilated room, we can have 5 times the room height between the openings. Now, the natural ventilation procedure in ASHRAE is really, you can say, a mixed mode ventilation procedure, as a mechanical system by default is required. However, there is an exception to the rule where we can either, if we have the opening area as a permanent opening area. We don't need a mechanical system. However, a permanent opening area would not be very energy efficient, you can say. Or you can have controls that make sure the windows are not closed during the occupied hours. However, this doesn't really allow for a lot of occupant personal control, which is often a great benefit of natural ventilation. With this slide here, I would like to illustrate the impact of using the different ventilation strategies. So as you can see here, we have 3 examples with single-sided cross and stack ventilation, and they are all based on this 4% of the floor area requirement of the opening area. And as we can see, there is a big difference where the ventilation performance for a single-sided ventilated space is much smaller than the ventilation performance of the 2 other ventilation principles. Therefore, you can argue that it doesn't really make sense to have 4% as a fixed rule for all cases. Now, in ASHRAE 62.1 2019, changes have been implemented to take the ventilation strategies into account. But not only this, it also takes the actual ventilation requirement of your project into account. So as you can see here, there are different categories for the cubic feet per minute per square foot, where you can actually define your ventilation requirement. Now, it should be mentioned that these tables of the prescriptive path still do not allow for a design based on cross-ventilated wind-driven flow. It's only based on thermal buoyancy with either a single opening or more openings with vertical spacing. And as we can see on this slide, compared to the 4% before, the percentages of the floor area that are required as opening area is now in many cases actually greater than the 4% from the earlier editions of ASHRAE. While if you have this spacing between the openings, you will have multiple cases where you need a much smaller opening area compared to earlier editions. It has to be mentioned that these tables are made on a temperature difference between inside and outside of only 1.8 Fahrenheit, corresponding to 1 Kelvin. So this is a very low pressure that we are basing these tables on. Now, another great addition to the new ASHRAE 2019 to the prescriptive path is the option of using the CIBSE AM10 method. And this method actually allows us to design our opening area or dimension our opening area based on the different ventilation strategies. And here we actually have cross ventilation with wind-driven pressure as an option. We also have the required ventilation rate as an input, you can see in the equations. And it's important for this method that we are defining the airflow balance ourselves, meaning for the case to the right here, you can see that the airflow going out through the roof needs to be equal to all the airflow coming through the facades. And this is something we need to define ourselves when using these equations. It's also important to notice that it's an assumption for these equations that the opening area we find is divided approximately equally between the facades, for example, here in this case with cross ventilation. So these equations are not based on having 80% of your opening area on this facade and 20% here. Now, it's common practice when you're calculating the pressure loss or when you're calculating the opening area to represent the pressure loss through the window by the discharge coefficient, which is denoted by the value CD here in the equations. Now, this discharge coefficient depends on the type of opening that you have, it depends on the opening degree of the window, and it also depends on obstructions in the window, such as box screens or insect screens. Yes. Now this CIBSE AM10 method is, I would say, a very great addition to the new ASHRAE 2019. And it's not only great for showing compliance, but it's also just an amazing method of designing your building and finding the correct opening area that you need. So I would recommend for everyone to look up this CIBSE AM10 guide and try it out for yourself. In the next part of the webinar, I would actually also argue how this CIBSE AM10 method is not only usable for the prescriptive path, but it can also be usable as a part of the engineered path. Now, in earlier editions of ASHRAE 62.1, the engineered path was described as a natural ventilation system designed or a natural ventilation system which was to be approved by an authority having jurisdiction. So I have a hard time to say that myself. So you can see that it's not very clear or very detailed, this description of what it actually entails, what you need to do in order to get this approved. But the new edition of ASHRAE 62.1 2019 has clarified and made this engineered path much more approachable. As you can see, it's divided into 4 different points, where the first point is based on the environmental conditions of the project. So if we're designing a building based on wind pressure and thermal buoyancy, we have to account for factors such as the outdoor temperature, the wind speed, the wind direction. And as it's also a performance-based compliance path, we also need to account for the internal load, which is primarily the ventilation requirement and the heat gains. The engineered path actually also requires us to account for outdoor contaminants, but this is only where data is available. Now we also need to look at the building design in relation to the airflow path and potential internal obstructions in the building. So we need to account for the pressure losses. And this is based on, for example, it's based on the inlet and the outlet, of course, but also features such as transfer grills and ducts, if that's in the design, or box screens. Now, the 2 last points here are very closely tied together, I would say, because the first point C here is saying we need to quantify the natural airflow rates. But we can't really do that if we don't have figured out our opening area yet. And this is what we also want to do with this path. We need to design our operable windows in order to achieve our desired ventilation rate. So an interesting thing about this engineered path is that all these requirements are based on the expected use of natural ventilation. And this is where this path becomes really handy, because we can then ourselves define the conditions and the expected use of natural ventilation, whereas the table shown before was based on a temperature difference of only 1.8 Fahrenheit. We can now define our own conditions. And I would like to show an example now of using the CIBSE AM10 method for this purpose of the engineered path. Now here we have a 2-story building with facade openings and clear story openings. As you may remember from 2 slides earlier, this equation here we can use to calculate our required opening area based on the airflow rate, based on the desired ventilation rate, you can say, and the pressure differences caused by both thermal buoyancy and wind pressure. So this equation can actually combine both. Now, I would recommend to start the design by only focusing on the flow driven by thermal buoyancy, because this is in general more simple. Designing based on wind pressure can really be a greater challenge, and this is mainly due to this wind pressure coefficient we see here, which is based on the wind direction in relation to the orientation of the windows, and it's also based on the location of the building in terms of surroundings. So all these factors we don't have to account for if we simply base the design on thermal buoyancy. Now, to calculate the wind or the pressure difference based on thermal buoyancy, we need to work with what is known as the neutral plane of the building. And this basically describes where the air is entering the building, as you can see through the facade, and where the air is exiting the building. So what we're aiming to avoid with our design is having a neutral plane which is too low in the building, because this would mean that the second floor windows are actually being outlets of old air transferred from the first floor. And this is something that we really want to avoid. To make sure the neutral plane is located in the right height, we need to look at the opening area of the clerestory in the top compared to the opening area of the facade windows. As a rule of thumb, the opening area of the clerestory should be approximately 1.2 times larger than the total facade opening area. Now, this pressure difference that we're calculating is now actually the pressure difference between each opening and the neutral plane. And as we are trying to calculate the opening area, we can locate the neutral plane in the desired location that we want, and then find the opening area based on this. So for the calculations I want to show, we have some quick design criteria. We have, let's say, a floor area of 1,200 square feet. We have a ventilation requirement of 0.4 cubic feet per minute per square foot. We have a temperature difference of 5.4 Fahrenheit corresponding to 3 Kelvin. And as compared with the table before, you can see this is a somewhat larger temperature difference. And this is also specified in the CIBSE AM10 that 3 Kelvin is a reasonable temperature difference to design according to, because in the end we also need to consider thermal comfort. So I want to base this example on this temperature difference. Then, to keep it simple, we have the most commonly used windows for natural ventilation, which is simply top hung outward opening windows. Now, as I mentioned before, with this method here, we need ourselves to define the airflow balance. As you can see, the outgoing airflow through the clerestories is exactly equal to the combined ingoing airflow through the facade windows. When we then calculate the pressure difference between each opening and the neutral plane, we can see that the pressure difference will of course be the largest between the first floor and the neutral plane, because the distance is the largest. As we have located the neutral plane somewhere in the middle between the second floor facade windows and the clerestory to ensure the correct flow, you can see that the pressure difference will be equal, but with a negative pressure for the clerestory as the air is outgoing. Now, with the information that we have our desired airflow rates coming into the building, we have our pressure difference, and we also have the discharge coefficient that I mentioned before. And CIBSE AM10 is specifying that 0.61 is the discharge coefficient to use for a top-hung outward opening window. So this is what we're going to use in this calculation, but usually it is somewhere between 0.6 and 0.7. Now, when we then enter these values in our equations, we find the required opening area for each floor. And as you can see, the first floor, the required opening area of the first floor is actually smaller than the required opening area of the second floor. And this is, of course, due to the larger pressure difference between the openings and the neutral plane. The combined opening area required for both floors is 55 square feet. And as we can see, the clerestory required opening area of the clerestory is approximately 1.2 times larger than the total opening area in the facade. So this is corresponding to the rule of thumb that I mentioned before. Now, it should be mentioned that for this design, because we are only designing it based on thermal buoyancy, we do not have to account for the different facade orientations. Therefore, we can just look at each floor as one zone. Now, these equations that we're using here are mainly based for a single cell zone, meaning that we have a completely unobstructed airflow between the inlets and the outlets. But let's look at an example if we start to consider the internal pressure losses of the buildings. Now, if these pressure losses becomes too complex, if you have too many features, we might need to utilize more advanced tools in order to estimate these correctly. Or you can, in worst case scenario, calculate the zones as just single-sided and see the thermal buoyancy or the stack ventilation to the clerestory as a bonus. But let's consider a case where we now have internal partitions between the inlets and the outlets. This means if we still want stack ventilation to happen in the building, we need to implement also transfer vents so we can have flow between the zones now. If we look at what we can do within the scope of these calculations without making it too complicated, this pressure loss of the transfer vents can actually be assigned to the facade opening area with this equation here. Now, the figure on the bottom here, the graph, shows the impact of the transfer vents on the resulting opening area that we use in the transfer vents. If we see this as kind of like a connected opening, this means also that we can still use the same calculation method as before without making it too complicated. What this graph shows is that if we have a transfer vent which is half the size of the original opening area in the facade, then the resulting opening area of the connection, which will actually only be about 40% of the original opening area. So it has a huge impact if the transfer vents are not large enough. We can see the larger the transfer vents become in relation to the opening area of the facade, the closer it will be to the original opening area, which is the 100% in this case. So the 100% is if we had the same case as before without internal obstruction. So we had a completely free flow. And if you have transfer vents which is approximately double the size of the facade openings, then it will be very close to just a normal unobstructed airflow. We usually therefore recommend the transfer vents to be approximately 1.5 times larger than the facade opening windows, as this is here where we see there will not be a huge difference in the resulting opening area going to a double the size. CIBSE AM10 also gives us a method of calculating the pressure loss of a duct system if this is relevant for a project. This can, for example, be if we want a noise reducing feature if the building or our project is located right next to a highway or a busy road, and we want to reduce the noise when using natural ventilation. In this case, the pressure loss is represented by manipulating the discharge coefficient that I talked about before. So this means that we can, again, in this case, also still use the same calculation method as before. We just need to replace the discharge coefficient that we find for our duct system with the discharge coefficient in our calculation, which before for the CIBSE calculation was 0.61. Now, this is where a lot of mistakes usually are made in the design phase, and the process of finding the opening area of a window is usually underestimated, and it can go very wrong with the design. So the calculations we made before were to find you can say the total opening area of each floor, but we then need to translate that into an actual number of windows. Now, the clear opening of a window is in general described as a minimum value of either the opening area A1 as shown here, or the sum of the opening areas A3 and A2. This is of course because no matter how much we open the window, we can never have an opening area which is greater than the hole in the wall. That's, you can say, that's very simple. Now, where it often goes wrong is with the design of the building. Here we have a very extreme example in the middle where the window, as you can see, is actually blocked by the facade, both in the side and in the bottom. So this is where if you can imagine, the window is located in an indent in the facade. This could be, for example, if you wanted passive solar shading, you wanted to use the facade as a passive solar shading. But if then we calculate the opening area simply based on, for example, A3 and A2, the sum here, we will completely overestimate the opening area. The correct opening area in this case will actually be, as illustrated here by the green line, this small opening area here, which is a part that is not blocked by the facade. This is also why if we have windows that are located right next to each other, they will actually function as one long window, and you will only have two sides of the window where the air can actually enter. Now, as I mentioned a little bit earlier with the discharge coefficient, it also takes into account the use of box screens in terms of the pressure losses. But box screens can actually also impact the clear opening of a window. But this depends again on the relationship between the sum of A3, A2, and A1, because the box screen will usually be placed within A1. And if the opening area of A1 multiplied by the porosity of the box screen is still larger than the sum of A3 and A2, then the box screen will have zero impact on the clear opening. It will still impact the pressure loss as the friction through the box screen is larger, but it won't impact the actual clear opening. Now, we also need to account not only for the placement in the facade, but we also need to account for the specific frame area of the window. And if it's an automated controlled window, we also need to account for the mounting of the actuator. So I want to show an example of this. If we consider the window dimensions in this table and compare it to the opening area required total opening required for the building that we calculated on before. If we make a very simple base calculation where we simply ignore the frame area and just calculate based on these dimensions, we will get an opening area of approximately 3.4 square feet for one window. And this will, in relation to the total opening area of the facade that we needed before, which was 55 square feet, it will correspond to a need of 17 facade windows. However, we at WindowMaster, we have actually made a tool that is called the Actuator Finder, which can help you find an actuator, as the name implies, but it cannot also actually calculate the opening area of a window, and very precisely, in fact. So it takes, as you can see here, the mounting conditions and the profile of the window into account, and you can specify the values here yourself. Now, based on these specified values and if we consider a top-hung outward opening windows, this tool will calculate the opening area as 2.4 square feet. And compared to our base calculation before, this is a reduction of 30%. And if we go back to our building, we will now need 24 facade windows. If we then look at a bottom-hung inward opening case, it will get even worse, where the opening area will now only be 1.8 square feet. And this is, again, compared to our base calculation, a reduction of 35%. And we will now need 30 facade windows for our building. So as you can see, the method of which we calculate the opening area of a window will have a huge impact on the performance and on the final design of our building. Because if we just calculate the opening area of our windows based on this base calculation, then we will in fact end up with a under dimensioned opening area for our building, and the ventilation performance will be too low. So we will have made a lot of good calculations before based on the CIBSE AM10 method, but because we calculate the opening area wrong, it will end up as, you can say, under dimension design. The last part, or actually the first part of the engineered path, but the last part in my approach to this path is the environmental data, where we have to account for the outdoor temperature, the wind speed, the wind direction, and the contaminants if the data is available. Now, the weather data, as you might know, we can gain from different databases, such as the Energy Plus database, which has weather files from all over the world you can download. But once again, we also have another tool from the Center for the Built Environment at UC Berkeley, where the awesome people has added another tool to the box that we can use, which is the CBE climate tool. And this also allows us to obtain weather data from all over the world, but it actually also allows us to directly analyze this data within the interface of the tool. And I would, if you haven't tried it out yet, I would highly recommend you to go see it for yourself. Now, I won't go into too much detail about the contaminants today, but there is a website, airnow.gov, which is a partnership among others, the Environmental Protection Agency and the EPA also have guidelines for the maximum values for each contaminants. But you can say that there is a lot of different locations, but of course, if it gets very local where you want to account for a busy road right next to your project, you would either need to measure this in some other way, or you would say data is not available if that's not an option. Now, I want to show a quick example of this to end the presentation with. I want to show a quick example of the use of the CBE climate tool. because it's just a really amazing tool, I would say. Just as an example, we are taking Sacramento as the location. You can say this is a location where there are good potential for natural ventilation, but it also gets very hot during the summer. So compared to other locations such as San Francisco or other West Coast location, it's not as favorable. Now, the design that we have made before is based on a temperature difference of 5.4 degrees Fahrenheit. That was, or 3 Kelvin. That was the design criteria that I set. So we know that when the temperature difference is above this criteria, our design that we have calculated will comply with the requirements, and when it's below this temperature difference, it will not comply. This way we can quickly filter the data within this CBE climate tool. And what I've done here is assumed an indoor temperature of 77 degrees Fahrenheit, because of course the critical moment of temperature difference will of course mainly be during warmer periods. So I've assumed a little bit of a high indoor temperature. And then I have filtered the data to show only the hours where the temperature is below 72 degrees Fahrenheit. So we have approximately this temperature difference of 5.4 degrees Fahrenheit. I've also filtered the data to be within the occupied hours, as I have defined as 8 a.m. to 6 p.m. Now this, I'm not sure why, but I could only show this figure in metric units. But nevertheless, what we can see here is all the colored hours where the system or where the outdoor data will comply with our design criteria. And it's not a surprise that the hours during the summertime is mainly the time where we don't have the necessary temperature difference to achieve our ventilation flow rate based on our design. Now we could make a whole spreadsheet where we calculate the ventilation performance or the ventilation rate for each hour throughout the year. That's not a very difficult task, but I would say that in this case, it's mainly the task to look if the ventilation rate will be above or below the ventilation requirement that we have defined for our building, which in this case was 0.4 cubic feet per minute per square foot. So all the hours here, it will comply, and in the summertime, it will not comply based on the temperature difference. And as we also have to consider thermal comfort, this seems very reasonable. Now, if we wanted to, we know our design, because we have openings on different facade orientation, we know that our design also allows for wind-driven cross ventilation. So if we, for some reason, wanted to check if these hours here during the summer could still be, our design could still comply with the minimum ventilation rate, we could also look at the wind speed, which can also be, again, presented by the CBE climate tool. And as we can see here, the wind speed is, in general, pretty sufficient during the summertime where the temperature difference is not sufficient. So we could, in theory, also base our design on the wind speed in the hours where the temperature difference is not sufficient. And of course, I would recommend you all to try out the CIBSE TIN guide. There's all these equations also I showed before, and you can calculate both based on temperature and wind for all the ventilation strategies and also for different design options. I just showed one example today, but there's a lot of possibilities. Now, this was all I wanted to share today. I have used, I think, approximately 40 minutes, so I hope it wasn't too long, but I would like to start the Q&A now and say, of course, thanks for watching and participating. And let's see what we have, if we have questions. We have the first question here from Larry Hodgins, who's asking if the ASHRAE 62.1 is a prominent ventilation standard used throughout Europe. And no, it's not, but you can say a lot of the requirements are very similar as these standards are finding inspiration within each other. So the ventilation requirements are often very similar. And I know the work group that the new requirements in ASHRAE 62.1 2019 is based on, or the working group that's worked on the new requirements. I know that a lot of people are from Europe, and so they have also of course given input that are very similar to the standards used throughout Europe. We also have a question about how we can assume an airspeed since the wind doesn't always blow. So as I understand this question, it's in relation to if we design our building or natural ventilation system based on wind. And it's true that the wind doesn't always blow. But you can choose to design your windows based on a very low wind speed and a very worst case scenario also in relation to the wind direction. And what will also happen in terms of wind design based on wind-driven flow is that when we have a low wind speed, the windows will actually still function as a scenario with single-sided ventilation, where the thermal buoyancy will still allow for cold air to enter the building and hot air to be exhausted through the building. So, but it is, again, if we go back in the engineered path where we have the description of the expected use of natural ventilation, we can also say, okay, if realistically most buildings in the US will be mixed mode buildings. So we can say when the wind speed is not sufficient to supply the required airflow to our building, we will not use natural ventilation. And that's the beneficial part of having a mixed mode system, that you use natural ventilation when it makes sense, and when it doesn't make sense, when you don't have the driving pressures, you use mechanical ventilation. We have also a question from John Nelson. In a mixed mode scenario, can the mechanical ventilation go all the way to zero when natural ventilation is present? Yes, that's I'm not a expert in the mechanical ventilation design, but in most mixed mode designs, it is the idea that when we use natural ventilation, the mechanical ventilation will be deactivated completely. We see some scenarios, especially during colder times, where you are making a combined strategy, where you, for example, if it's very cold outside, you're supplying the building with 2/3 mechanical ventilation, and then the last third with natural ventilation, because then you can kind of manipulate with the heat loss of the building, the balance between the heat gain from the occupants and the internal loads and the heat loss through the windows. And you can make the calculation to see at which outdoor temperature will it not be beneficial to use natural ventilation, even as 1/3 of the design anymore. But that was me going a bit sideways. In general, the idea is that the mechanical system, it will be deactivated when the windows are open in a mixed mode system. I also want to mention just quickly that we have created different calculators on our website. I mentioned the actuator finder before, that can help you find an actuator, but also calculate the opening area. We also have an air change calculator, which based on a given design, if you already have a design, can calculate the ventilation performance in terms of an air change rate based on your design. Then we are also soon launching what we call a dimensioning tool, and this is actually based on the CIBSE AM10 method that I have been presenting today. So if you don't have, or if you don't have your own spreadsheet yet for the CIBSE AM10 method, you are very welcome to try out our tool when it's up and running on the website. I also want to mention that we have some upcoming webinars in the future, which will address subjects such as automated versus manual control of operable windows, so the benefits of each. We will also address the natural ventilation potential throughout North America, so in the US and in Canada. So we are developing an approach where we can figure out an estimate of how much you can use natural ventilation in each location based on some predefined assumption and criteria. We of course also have our contact information here on the right. As I mentioned before, I'm located in Copenhagen, Denmark. You're very welcome to contact me with any questions you may have, because today, of course, the presentation was only a small part of this universe. I only presented one way of calculating with the CIBSE AM10 method based on thermal buoyancy. But there's also, of course, a lot of different ways to approach natural and mixed mode ventilation in a building. But you are also very welcome to contact my colleague Mia, who is locally placed in the US. She's on the West Coast in San Jose, actually, and she also knows, of course, a lot about these topics. And if you want to know more about automated technology for natural ventilation, you're very welcome to contact Mia. Now, I think if there's no more questions, it might be a good time to end the webinar. And of course, this is, if there's something you think about after the webinar that you want to ask, of course, you're very welcome to contact us. And the webinar will be sent as a recorded version to your mail, and it's also available on our website. So so you have the possibility of, if there are some details you miss, I know some parts of the presentation have maybe went a bit quickly, but you can rewatch it and ask any questions you may have. But if that's it, I think I will end the webinar today. I hope you enjoyed watching, and yes, have a nice day, and I hope to talk to you soon and have a chat about natural ventilation and in general building performance. So yes, I will say goodbye and have a nice day.